semiconductor diode. The semiconductor diode is a nonlinear resistance. Its resistance value depends upon the applied voltage. The forward resistance offered by the semiconductor diode is low, while its reverse resistance is quite high. The ratio between the reverse to forward resistance of a typical good specimen must be more than 1000. This is known as aspect ratio or figure of merit. The germanium point contact diode, often known as signal diode, is formed by a stiff phosphor bronze wire welded to an N-type crystal. Forward biased diode shows low resistance. When it is reverse biased, shows high resistance. Sketch shows lab experiment germanium diode forward biased mode. In this laboratory exercise, let us study the features of point contact germanium signal diode type YA79 or 1N34. With a protecting resistor of 100 ohms and supply voltage not exceeding 1.5 volts, the maximum forward current is restricted to 15 milliampere under worst case situation. Lab experiment when the germanium diode is reverse biased. The reverse bias voltage is increased to 30 volts and the recorded leakage current quite small, refer figure. The silicon diode is found quite useful as rectifier in power supply circuits because it permits fairly large current to flow in the forward direction. That is, the diode acts as a closed switch when it is forward biased and as open switch when it is reverse biased. It can be constructed to withstand higher reverse bias breakdown voltages and to exhibit low reverse bias current. They can handle high forward currents. Experiment on silicon diode. It may be noted from the curve that its forward voltage gets steady at or near about 0.75 volts. The silicon diode can withstand 400 volts or even more in the reverse direction. Thus, the device is ideally suited in rectifier or power supply circuits. The Zener diode. The Zener diode has almost constant voltage drop over a wide range of current flow and can be manufactured to provide a choice at voltages this phenomenon occurs. The constant voltage drop of Zener diode is actually the reverse breakdown voltage that is characteristic of semiconductor. This phenomenon, commonly called Zener breakdown, occurs when a large enough voltage is applied across a p-n junction in the reverse direction, cause electrons to break out of covalent bonds and become free electrons. The voltage at which this occurs is very sharply defined. That is, the reverse current flow increases very rapidly with only a small change in voltage. This is what gives the Zener diode its great value in electronic applications. The forward characteristics of Zener diode is shown in figure. Zener reverse characteristics is given in figure. Zener voltage regulator circuit is shown in figure. The voltage across the Zener well settled at 12 volts and the current diverted through the device would be around 50 milliampere. as the load resistor value is reduced in steps of 1K, the load current would get progressively increased. Zener diode current proportionately reduced while the Zener output voltage remains constant at 12 volts. This lab exercise demonstrates that the load current range of 1 milliampere to 80 milliampere, that the Zener output voltage remains constant at 12 volts. Silicon controlled rectifier, SCR. The silicon controlled rectifier, SCR, is a 4-layer NP solid state rectifier which has 3 electrodes, an anode, a cathode and a gate, which serves as control element. The SCR differs from the 2-element diode rectifier in that it will not pass any appreciable current though it is forward biased until the anode voltage equals or exceeds a value called forward breakover voltage, VBR. When VBRF is reached, the SCR switches on. That becomes highly conductive. The value of VBRF can be controlled by the level of gate current. The gate provides a new dimension in rectifier operation by which low levels of gate current can control high levels of anode or load current. The silicon controlled rectifiers are very useful in AC circuits where they may serve as rectifiers whose output current is controlled by small gate current. This typical application is the use of SCR to operate and control DC motors or any DC load from an AC supply. The DIAC. A DIAC is bidirectional avalanche diode which can be turned on by either positive or negative alternation of an input AC. This solid state device, like the conventional diode, has 2 terminals, MT1 and MT2. The circuit sketch and junction diagram of DIAC is shown in figure. The junction diagram points up the very different construction of a DIAC as compared to that of a regular silicon diode rectifier. It has 2 junctions, junction 1 and junction 2, whereas a diode has only 1 junction. The DIAC also differs from a bipolar transistor in that the concentration of impurities at the 2 DIAC junction is the same. In a transistor, they are different. The equal doping levels in the DIAC helps to explain the symmetrical current characteristics of the device. When the voltage across the DIAC has increased to plus VB0, avalanche breakdown occurs at the reverse biased junction. The DIAC current increases dramatically at this point and is limited only by the resistance of the external circuit. DIACs are used as triggering devices in light dimming circuits, in heat control, motor speed control circuits, and in similar applications. The TRIAC. The TRIAC, like an SCR, is a gate-controlled silicon rectifier, but unlike the SCR, the TRIAC has bidirectional current characteristics. The TRIAC has 3 terminals designated as MT1, MT2 and gate. In one polarity of supply input, the TRIAC remains in an off state until the breakover voltage is reached. When it turns on, in its on state, the voltage across the TRIAC drops to a low value and current is limited by the parameters of external circuit. When the polarity of supply input is reversed, the same off to on state occurs and the current through the TRIAC is also reversed. Gate current will trigger a TRIAC whether the gate is positive or negative relative to terminal MT1. regardless of the voltage polarity across terminals. TRIACs are used in light dimming control circuits, in motor controls, in heat control circuits, and in other industrial applications. Silicon photo devices are light sensitive devices which convert the light signals into electrical signals. The photosensitive property of semiconductor is employed in a photodiode to convert light energy to electrical energy. When light shines on the reverse biased photodiode, whole electron pairs are created. The movement of these whole electron pairs in a properly connected circuit results in current flow. This current is proportional to the intensity of light and is also affected by the frequency of the light falling on the photojunction. This current cannot be used directly in control applications. After amplification, the photo current may be high enough to be used in a control system.